All right, guys, my clock says it's time to rock and roll. Glad to see you here. I hope you're all doing well. We've made it to Thursday and just about ready for another weekend. I have to tell people I start working on Tuesday and I stop working on Thursday. My weekends are long. But actually, I'm usually working a lot more than that. It's just the way this goes. Quick reminders. First of all, there's a homework assignment due tonight. I think a handful of you have already turned it in. If you haven't, no worries. I have office hours after class and I'll be around all evening, except for a dinner break, which I usually take at 7. So for about an hour to an hour and a half, I'll be gone, just kind of resetting myself. And then I'll be back by 8:30 and I'll hang around all night. So if you've got questions, feel free to jump into Zoom with me or in person, whichever is better for you. That's for tonight. I'll get those graded. I did get the first homework graded finally. And now I should be hopefully on a little bit better schedule to keep up with the grading. If you have questions about the grading, by the way, you're always welcome to talk to me. Don't feel like you can't ask me about something. If you lost some points somewhere, you're like, I wonder what happened, or you just want to ask me about it, we can talk about that. I will, of course, post the solutions, and you can also be looking at those to kind of figure out maybe how I approach some of those things. The next homework that you're going to have after tonight is a little bit shorter assignment. It's going to be due actually on Tuesday. I tried to switch to Tuesday this week, and it just wasn't going to work. But let's get this next one done by Tuesday. The reason for that is then I want you to have a couple of days to study for the quiz. So we'll take a quiz next week on Thursday at this time, right at the start of class. So you want to be on time to have the full time. The quiz, I think I'll write it down again just to be 100% sure. The quiz, which we're going to take next Tuesday. What is today's date?
The 11th.
The 11th. So the 18th is the quiz, and it will be based on chapters 2 and 3. Which is going to basically be homeworks number 1 through 3, including the one you're going to do for Tuesday, and group works number 1 through 3. We've already done group works 1 and 2. We're actually going to do number 3 today. So you'll have several things to be looking at here for the quiz on Tuesday or on Thursday. The quiz is on Thursday. Okay, question.
On the homework solutions, sometimes if there's a problem that's very, very similar and uses the same technique as the one before it, you say, well, I have a similar technique, this modification.
Yeah.
Can we do that on our?
Yeah, that's okay. I do think it's helpful to write it out though. Personally, if I was learning it for the first time, I probably would just to get in good habits.
Okay.
But yeah, that's okay. You can refer to something you did on a different problem. I totally don't mind that. Okay, so does anybody have any questions about any of that? Quiz next Thursday. We got homework tonight. We got homework on Tuesday. That ought to be enough. Keep us busy. So I'll leave it at that. Let me remind you, we are going to finish chapter 2 today. And I am just on this very last topic, which is combinations of multisets. And so just to remind you again, we are looking at problems where the order that the objects are in does not matter. So there's no first object, second object, third object, and so on. So I don't usually think of drawing slots for that, right? So usually when things are put in an order, like a photograph or a license plate, I would draw slots. But if I'm just talking about poker cards or buying fruit, which was the analogy I gave for this on Tuesday, I tend not to draw slots so often in that situation. And then in addition, here we're talking about the situation where repetition is allowed. So you go to the grocery store and you can repeat an apple or a banana as many times as you want. So that's the context, combinations of multisets. And the theorem that I've kind of spelled out here in the middle is just giving us sort of the answer for how many arrangements there will be in this context. So if we had K types of objects that you could take as many of as you wanted, so infinite supply. You have K types of objects and you want to end up with R objects in total. Okay, and you're making combinations of them, not permutations, right? The order does not matter, so that's usually associated with combinations. But the number of R combinations of your objects is given by this formula right here. R plus K minus 1, choose K minus 1. So we're not surprised to see the combination notation, since that's the type of situation that we are in. It's a little bit of a surprising formula, I think, subtracting 1 here kind of thing. It looks a little funny. Well, that's just because if you have these K types of objects, you only need sort of K minus 1 dividers between, or bars as I call them here, between those different types. Okay, so I talked on Tuesday, right, about how you can make a string of stars and bars, where the stars represent the objects that are in a particular bin, and the bins are separated by the bars, and the number of bars is the K minus 1, and the number of objects is the R. So the full spectrum of what you have to do is take all of these stars and bars, however many positions that would be, and you need to fill either the K minus 1 bars or the R stars. You need to fill those in by choosing slots for those. Okay, so in that sense, eventually we do have slots. I mean, I said earlier, I don't usually think of drawing slots when the order doesn't matter, but in the way that we've recast these problems as strings of stars and bars, now all of a sudden we do have slots again. So that's just something to keep in mind. Okay, we did one basic example of this on Tuesday, but I want to show some variations and give you some maybe slightly more challenging examples of it. So we have a few things to practice on. But before I do that, are there any questions just kind of about the summary here? This is just like a recap, basically. Okay, so far so good, I hope. So let's do another example. I only had time to do one example on Tuesday, and I think it's probably worth a little bit more than that. So let's come over here and talk about another example. So let's ask this question. How many ways can we buy 18 pieces of fruit? And I'm going to remind you, we're going to use the same setup from the one we did on Tuesday, which is that we have apples, oranges, and bananas. So there are 3 types of objects here. The K value would be 3 in this example. But this time, so I think I asked that question just like that on Tuesday. And all it was, oh, well, R is 18, K is 3, and you come over to your formula here and you get 20, choose 2. Okay, so that's fine, but I'm gonna now throw a little bit of a twist in here, namely, if you must, so there's a constraint, I'm gonna give you a constraint, if you must buy, so your family sent you to the store and they said you must buy at least 3 oranges and at least 4 bananas. So they're basically telling you, you must do that. Okay, so obviously with this extra constraint, we would expect our answer to get smaller now. Right, so the 20 choose 2 that we came up with originally on Tuesday, this is probably going to force us into less choices. We must take 3 oranges and we must take 4 bananas. So how do we want to think about that? Well, let me suggest an idea. So you were sent to the store to do this, and you must take at least 3 oranges and at least 4 bananas. So you know what I'm gonna do? I'm gonna go into the store and I'm gonna go get my 3 oranges and my 4 bananas and walk them out to my car before I do any other shopping and just make sure that I've got that constraint done, right? So I get my 3 oranges, my 4 bananas, I take them out, and so far I didn't make any choices. I mean, I basically didn't have a choice. I must take at least 3 oranges and 4 bananas. So let's put 3 oranges and 4 bananas in our car and go in and start over. But now when we're starting over, we no longer have any constraints on us because we've safely put the fruit that we're required to have in our car. But what has changed is that out of the 18 pieces of fruit, I am now only looking to get 11 more pieces of fruit, right? So all that this is, guys, is it's really just the same thing again, except instead of R equals 18, R is going to equal 11. Okay, so let's write that down. It's just that simple. So the solution here is after satisfying the requirements of at least 3 oranges and at least 4 bananas, we are left with, I'll just write it as 18 minus 3 minus 4, which is equal to 11 stars. Because we could buy more bananas or oranges, or I mean, at this point, we could do anything. So 11 stars and 2 bars. So we still have the 2 bars. And so I'll just say by stars and bars. By stars and bars, we're going to get an answer, which is going to be 11 plus 2, choose 2, which is 13, choose 2. You could also write it as, of course, as 13, choose 11. Because remember that n choose r is always the same as n choose n minus r. So I actually usually will prefer to think of the answers in terms of choosing the bars because the number of bars doesn't change very often. And so if I already know that I'm always choosing 2, it's just a little easier. It's not that it's wrong or less correct to put the 11 down there, but it's just easier to always have that same number on the bottom of your combination expression. So is everybody on board with that? So 13, choose 2. Okay. That's when we see at least something. So at least 3 oranges and at least 4 bananas. Now let me give you another variation that's maybe a little bit different. So as another example, I'm just going to say how many ways. And I'm just going to assume all the same assumptions. 18 pieces of fruit. We have apples, oranges, and bananas, right? So how many ways if we must buy exactly 2 apples. We must buy exactly 2 apples and at most 9 bananas. So the at least condition is not here anymore. I've now changed it to something else. So exactly 2 apples and at most 9 bananas. But we're still going to end up with 18 pieces of fruit. We're choosing between apples, oranges, and bananas. So what would you probably do when you pull into the parking lot first on this one? What would you maybe think to just take care of right away? Let's just go get the 2 apples. There's no choices to be made. You are required to do that. Get your 2 apples, take them back out to the car. At this point, you would be left with 16 pieces of fruit aside from the 2 apples. But of those 16, we would be looking for only oranges and bananas. Okay, so after removing 2 apples, we need 16 fruits from bananas and oranges. Well, let's say oranges and bananas. Keep everything in the same order. From oranges and bananas. Now, this problem, I've made it so small that you could just kind of be not even a combinatorics student and figure this out. I can take 16 oranges and no bananas, or I can take 15 oranges and 1 banana, or 14 and 2, 13 and 3. Basically, the two numbers have to add up to 16, and you can figure out that there's 17 ways for that to happen, right? Everything from, you know, you can have 16 here and 0 here, or you can have 15 here and 1 here. It's because there's only 2 things, right? And you can go all the way down, maybe you have none of these and 16 of these. You could do any of those. And then you'd have to realize that we can have at most 9 bananas. So at some point, wherever this was, I guess this would be 9 and 7, right? These would only be the ones that you would be allowed to have. And you could just count these, there's 10 of them. Okay, so the answer to this question is 10. But let me just give you another way to think about it, because this is gonna be too simple for a lot of things, right? You're not gonna be able to just, what you're really doing here is literally enumerating all of the possibilities, because it's such a small number of them. It won't always be that simple. So does somebody have another idea that would be maybe a more broadly applicable approach at this point? If we need to have 16 pieces of fruit, and we need to have at most 9 bananas. Kevin? The violations, we can think about that, subtracting the violations idea, right? Yeah, I love it. So you could take all the possible ways of choosing them, which actually would be all of this, and subtract out the violations. That's exactly what I would do. So now we subtract violations from the total. And let's see, what is the total? The total, at this point, we're only doing oranges and bananas, right? And so we would have 16 stars, and we would only need 1 bar to separate oranges from bananas. The apples are gone, right? So it's just 1 bar. So in this case, the total, let's talk about the total first. For the total, we would have 16 stars and 1 bar. And so our answer would be 17, choose 1. Okay, so that's the total. Again, these numbers are coming out so small that you could just write the whole thing out, and I don't want you to only do that, because sometimes it's too much to write out. But then let's look at the violations. The violations would be fruit choices that have at least 10 bananas, right? So this would be combinations with at least 10 bananas. And so now we're back to the earlier type of problem. So we are showing up to the store, we need to buy 16 pieces of fruit, we need at least 10 bananas. So we're gonna go get those 10 bananas first, take them out to the car, we haven't done any choices yet. We come back in, we only need 6 more pieces of fruit, right? So there's only 6 more pieces of fruit. That would be 6 stars and 1 bar this time. And so that comes out to 7, choose 1. And now we just do subtraction. 17, choose 1, minus 7, choose 1. Okay, so the answer would be 17, choose 1, minus 7, choose 1. Of course, 17, choose 1 is 17, and 7, choose 1 is 7. And so the answer is 10. And that's exactly what we came up with when we wrote them all out. So we would have 10 ways to do this, guys. It's a pretty small number now. It's a pretty small number. Okay. Does that make a little bit of sense? Okay. So that's just a couple of examples with buying fruit. Let me show you another problem where this stars and bars technique kind of can show up in sort of a more raw mathematical example. What if I gave you an equation I wanted to solve? So consider solving, let's say x1 plus x2 plus x3 plus x4 plus x5 equals 2025. If x1 has to be at least 21, x3 has to be at least 6, x5 has to be at least 3, and all of the xi's are integers. They are integers. Sorry, I want to say that they're non-negative integers. So let me just write it this way. They're either 0, 1, 2, 3. I'll just make that as a set. So we're not going to have any negative numbers for this. So this is a real world type of thing. You're not using negative numbers. You've got 5 different quantities that need to add up to 2025. Okay. So this is actually just like this. You could imagine, here's how many bananas you have, here's how many oranges you have, here's how many apples you have, here's how many cherries you have, and here's how many pears you have, right? You can basically think of it as just fruits. Each of those variables represents fruits. And you, again, for your solution, you can create bars and put your X1s, in this first section. And then in the second section would be the X2s. And then the third section would be X3s, and then X4s, and then finally X5. So you could fill in stars there, right? And the number of stars should be 2025. So 2025 is the number of stars. You can see that we have 4 bars, right? But we are required to have at least 21 in the first variable. So that would be 21 apples at least, right? At least 6 bananas and at least 3 pears. So we just treat this the same way. We go take care of, basically what you do is you knock these numbers off from the total number of stars. You see? So for the answer, all you have to do, guys, is, you take stars plus bars, choose bars. I have 4 bars on the bottom, and on top, I'm going to have 4 bars also. I'll put that there. And the question is, how many stars are there? Well, this would normally be the number, but I'm taking away 21, 6, and 3, which is actually 30. So if I subtract 30 from 2025, well, let's just write that down. 2025 minus 30. And then plus 4. So that would be 1999, I think. Choose 4?
Yeah.
Okay, whatever that number comes out to be. So that would be the answer there. So something like that.
Where was the 30 coming from?
The 30 is, here's 21, 6, and 3. Those are adding up. So just to be totally clear here, well, I should use a star. It'd be a little bit confusing. This 30 is just adding up the 21, the 6, and the 3. In the same way that over here, we subtracted 3 and 4, which came from adding these 2 numbers up here. That kind of works the same way. Sometimes you can get conditions working in both directions, so at least a certain minimum, but also with some other variable, there could be a certain maximum. So let me just do another example. I think I have enough room right here to just kind of combine that together a little bit. Let's see if I can just phrase this as well. In the above, in addition, assume that x3 is at most 100. So x3 has to be at least 6, but at most 100. So I'm saying throw that as an additional condition. You with me? So the idea here is, of course, you can take your previous answer and subtract the violations again. It's kind of back to Kevin's idea. So what we would do is we would take, for the solution, we would take 1999, choose 4, and we would subtract violations. I'm just gonna write it like that, and you can do this too if you want when you're writing these up. So you just subtract violations from the 1999, choose 4. So the violations would be, let's just write this down, 1999, choose 4 minus, so the violations would be anything where the x3 was at least 101. So that would mean you took at least 101 bananas, right? So those stars would go away. So if I take those stars away, what am I gonna have here? Well, if I subtract 101 right here, this is going to be 1898, I believe. Take 1999 and subtract 101.
Yeah.
Okay, but is that correct?
I think the answer is 1894.
Be 1894 plus the bars.
Yeah.
Okay. So the issue is that I already took at least 6 bananas. So those bananas already ended up in my car and they are already incorporated into this, right? So whatever I'm subtracting should be things that are being taken away from this, which would be arrangements where, you know, we've already accounted for the fact that we've put 6 bananas in the car. So if we've already put 6 bananas in the car, then that means that we should take at most 94 more bananas, not 100. So this condition says x3 is at most 100, but we've already piled 6 bananas into the x3 bin. So we should have at most 94 more bananas, and so the violations is actually not to subtract 101 from the number on top, but to subtract 95 from the top. Is everybody following that? Because we're supposed to have at most 101 bananas, but we already, this number is already assuming we had at least 6 of them. So we can have at most 94 more. And the violations to that would be having 95 more. So I need to subtract 95 from this number, not 101. And so this should actually be 1904, I believe. So I'm just gonna add something here. This is since we can have at most 94 more bananas. Not bananas, I'm sorry. At most 94 more for x3. So in other words, the x3 is at most 94 at this point. It was a given as being at most 100, but we've already, in this universal total, we've assumed that we've already put at least 6 on the x3. And so that means we only have room for 94 more at most. So the violations would be having 95 or more. You with me? If you don't like that, never fear, I have another way to show it to you. Let me show it to you another way. You might like this better. What we wrote over there is just fine, but there is another way to do this, which is just as fine, and it's the following. So I'm just going to redo this example again. So again, what is the example? We have x1 plus x2 plus x3 plus x4 plus x5 equals 2025. And the condition was x1 is at least 21. x3 is between 6 and 100. And x5 is at least 3. So there's another way to do the problem that's a little more like mathematically streamlined. And what it is actually to do a change of variables. And the way you do it, this is sort of an alternative solution. Maybe you like this one better, I don't know. I'm gonna try it out on you. The alternative solution is to change variables. And what we do is we let y1 equal x1 minus 21. Now, if I do that, then that would mean that the y1 is at least 0. So you take this condition here and you just subtract 21 to make a new variable, which we're going to call y1. All right. And the condition that x1 is at least 21 is equivalent to saying that y1 is at least 0. Okay. For y2, I would just let it equal x2. There's no mention of it in anything that we wrote. So I'll just leave it the same. y3 would be x3 minus 6. If I do that, then y3 now is at least 0 because of this condition. Right, but you can also see that since x3 is less than or equal to 100, then y3 should be less than or equal to 94. See that? I mean, you can add this 6 to the other side, and you'll see that x3 is less than or equal to 100. It's equivalent to the original condition. We would just let y4 equal x4. No change there. And then y5 would be x5 minus 3. And that would be at least 0. So what is our new problem in terms of y? Well, what we can do is, first of all of the y's are at least 0. And what are they adding up to? We can sort of substitute them in to what we had originally. So for example, the x1, so I'm gonna take this equation and I'm gonna replace it down here. x1 becomes y1 plus 21. And then x2 becomes y2. And then x3 becomes y3 plus 6. x4 just becomes y4. And x5 becomes y5 plus 3. All of this is still equal to 2025. But what I'm going to do is I'm going to take all of these constants that are now showing up on the left side and combine them with the 2025. So what do we have? We have 21 plus 6 plus 3, which is 30. And so what we end up with then is y1 plus y2 plus y3 plus y4 plus y5 equals 1995. And now the conditions that we have are that all of the y sub i's are greater than or equal to 0. And we're going to subtract, we're going to have one extra condition, which is that the y sub 3 is at most 94. Okay, so with that labeling of the variables, now this is a little bit more back into a standard problem. What you're going to do is you're going to say, well, without the constraint on y3, we have a standard problem of, the total would be, the number of stars is 1995. We have 4 bars and we're going to choose 4 bars. Right? And then for the violations, Now it's just a little bit easier to think about the violations. Violations would just be if y sub 3 was at least 95. That's it. So you go take 95 out of the total, so that leaves you with 1900 stars, and you still have the four bars, and so you get 1904, choose 4, and we're getting exactly the same answer that we did sort of just thinking about it over here. So if you like to do it more using the actual change of variables, this is how you could do that, right? So then the answer is just subtraction. We get 1999, choose 4, minus 1904, choose 4. Yeah, which is the same thing we said earlier. Same thing we said the first way we kind of worked it out. Somewhere here. Yeah, does that make any sense? Seem reasonable? Okay, any questions kind of on this stars and bars thing? Actually, this change of variables approach is also kind of nice if you did have negative numbers floating around. Because it's kind of awkward to think about, you know, doing it this way, you're like, okay, so negative numbers means I'm going to go take some apple from the trunk of my car and put it back in the store or something. It's like reversing the process, and that's a little bit harder to think about. But the change of variables will work just fine if this condition was, you know, x1 is at least -5. You could create a y1 that would have been x1 plus 5, and then that would have been greater than or equal to 0. So it works nicely for problems where negative numbers make sense. Obviously, with the fruits example, you wouldn't be thinking of it that way. But if it's just a raw math problem like the one we're looking at here, that kind of change of variables could be useful. So it's worth being comfortable with this way of looking at it as well, I think. Okay. Gosh, I've kind of done the examples I wanted to do. I think maybe what I'm going to do next is let you guys practice a little bit. Okay, I've got some group work here. There's 2 problems. I definitely want you to do problem 2, which has 5 parts to it. I really want everybody to have a chance to think about that. So you could start with that, unless, you know, I mean, I'm not telling you what to do. You can do whatever your group wants to do. But let's take, you know, a little bit of time and get you up out of your chairs today, and I will come around and give you guys a hand. You should have markers anywhere around the room that you want. Might be some extra too. I'm not sure, but grab 2 or 3 people if you don't mind, and see what you can do with these problems. And let's talk about it. Okay. I'll go ahead and erase up here.
Fighting the blade.
How are you guys doing? Good, okay. Is it hot outside?
Yes.
They said next week is gonna be worse. Yes. That was supposed to be this.
In the morning, it was like saying, and you know.
I know, I
The
thought.
skies were great.
I was thinking, oh, it's gonna be kind of nice, and then, you know, it was always in summer. I didn't even, probably by the time I got out of here.
That's it, that was good. It's full again.
I said the other day, yeah. Well, hey guys, I'll get excited to win. Hi.
How many of those?
Hi. The video. Like, well, yeah. I don't know. We always have to do, we're always recommend.
When I was in the school, you guys were doing it.
Oh, two.
I can see. You said it was over.
Oh, and I got it. Wow. You writing cards?
Yeah, Jay mentioned.
Like Maria.
So
What?
you're Ashley.
I'm Ashley.
Right, okay, and is here, Maria, and Al. Okay, awesome, great, very good, thanks.
It's 7 fire stations. And there's one truck.
Like, wait.
People forget that.
No, it's gonna be like, if you're, I thought you were gonna tell me the reverse, like, no, it's actually.
No, you're good.
You guys aren't gonna make any mistakes, right?
No, we're.
Oh, of course.
Okay, good. This is gonna be all over the internet, so. Anyway, if you need some help, I can help.
Send outside one of those trucks.
Well, there's 21, right? 21 trucks and 21 fires.
Like, if we're assuming.
Are you doing a movie? Oh, I thought we were going to.
Or multiple.
I mean, let's build our confidence first.
Yeah.
Oh, yeah, let's do the one here. That's work here. I like it.
Trucks at the beginning, some leftover trucks. You suggest to me that somehow they're important. Because the trucks that we started with. And then you see that our first later. And that
Yes.
suggests that.
So,
Later trucks. Don't think we want. And you can put like this fire trucks.
it's too bad. So it's-
So if I'm the dispatcher, tries to out these trucks. Well, it really doesn't matter which truck I put to this fire, because I always. Really
No,
matters.
this says how many streams are based on G four, so we can add them together.
Yeah, because they are mutually exclusive. They cannot both start with G.
How many trucks go to the first fire? How many trucks? go to the- Oh, don't you, all eight. A zero.
There is 10 letters.
The part A.
Yeah.
One.
We could send all 21 trucks to the fire.
No, we did it. Some parts we did it, but it was different. There was only,
We thought every fire would get at least one.
And I think that's part.
fire station is posted by
Like
specified
that,
version.
fire required to have at least,
The fire station on the
We're just gonna have a free roll and just, send the truck in the fire.
Is it gonna be 21 factorial?
Any-
Because the 21 fires, are we
No.
spending one at each one?
I'll
Oh, it's
come
a
back.
combination.
I'll come back to it.
Yeah, 20, do we have to guarantee one truck is going to each fire or?
Yeah.
Not on part A. On part A, no.
We can have all of them go to one
They can
fire.
all go to one fire. It's
Oh,
part
wait, what?
B. Part B says each fire has to have at least 2 trucks.
So what should that be?
Okay,
So we're not-
We can let the whole, we can let 6 of the fires burn the town down, if we could just have all of them go to the first.
Okay.
I don't think it's 21 factorial.
No, I was thinking if we had to put one in each.
Oh, okay, that's right.
Yeah.
For part A?
Yeah.
It's gonna be 21 stars. So 7 fires.
So,
There's 7 bars or 6 bars, right?
Wait, 21 to 7.
For 7
No, if you
stars.
start 6, then it's 6. Then it's 21 trucks.
21 trucks. That's fine.
So for each truck, is sent, each truck can go to.
We have, you're right. It's gonna be X1 plus X2 plus X3, 7 slots.
But I'm doing my
Fires.
So if you wanna write it to the slots, you can write like.
double check that.
Yeah.
We can write it like an equation. Kind of X1.
That's gonna be the right answer to some.
Oh, take one.
So 7 fires, right?
Yeah.
There's 21 trucks total in sense.
Yeah.
There's 7,
And then add it.
7, and we have 6 bars. So 7 plus 6.
So this means we had.
It's kind of like the fruit, it's like the fruit, all the bananas are identical, right? All the orange are identical. So we have 21 identical trucks and then 7 different locations.
Six fires.
So what's that? That was 21. We have, we have seven objects that are K, right? Under K. And there's 6 bars, that's what. Right. So we do 7 plus 6, which is 13. Choose the number of bars. Oh, wait, no, 21 objects. Yeah, 21 objects are yes. That's 27. And then 6 bars. Stars plus bars.
Oh, these are the smarts.
Stars.
Yeah.
Was it
Yeah.
all?
That's our secret.
It's a risk.
Yeah, oh, they have. Okay.
6 bars.
Oh, 6 bars.
Good job. You guys feel pretty comfortable here on
The fire trucks are
Number
identical.
one.
And each fire.
I think you're right, yeah, there's 10 levels, so that's 10 factorial, and then you're dividing by 9. Crazy going on there, and then part of you have 2 different cases that just add. Looks really good to me. All right, number 2 is divide the way you're starting.
21.
Okay.
And then we still have 6 bars.
Yes.
Yeah. Yes.
Yeah.
How are we doing so far?
This looks fantastic. So it's a stars and bars problem with 6 bars and 21 stars. Now, on the second one, we take it. Okay, right. These 2 trucks have to go to each fire, that just means there's a.
7 items.
Okay, 7 there, but then this becomes 7 plus something. So don't forget, you still have to add, you still have to add the bars here. Which becomes 13. And you can see that, 27 went down to 15 because you took away 4.
So we could get rid of.
Okay, good job, good job.
Now, this is the one that's. So because they're all the same.
Like this, this came out of.
Yeah. It's a,
Oh my God.
You get rid of.
So then. That we have.
He's over here writing visual.
They're really.
Yes, it is fermentation. I think what makes matter, it's gonna matter which fire. So this is 21 factorial times 20 factorial. And we have to set 1 to fire, no, right? We have 7 no.
So you need.
So it's the fermentation, you have 21 objects fermentating in 7 places. So isn't that 21 factorial? It's the same 10 factorial n minus r factorial.
That implies.
Oh, no, wait, I was thinking if the drop had, 7 different options.
Oh, so you were right. Yeah. So that's what I was thinking. You have your 21 trucks, right? And each of them have 7 options.
Yeah. Oh, no, yeah, like the truck had the fire.
Yeah, that's how it should be, because, because the first truck, he has 7 fires in his back. And then the second truck is 7 fires, and then.
Other than that. Does somebody want to explain that one to me? The trucks are all the same.
Mr. John, I'll just read that.
Well, I'm trying to
So
Yeah, it sort of goes.
Okay, each truck has 7 different options.
Okay.
So then.
The number of 7.
And they're independent of each other, because where the first truck goes, the second truck can still go anywhere, right? The third truck can still go anywhere. Let me ask you this, would it have been possible to, so instead of each truck choosing which fire to go to, which is what that number gives you, which is the correct answer. Would there be- is it possible to think of it in reverse and say, let's have the fires choose the trucks?
Right here shows it's 7 to.
And each fires, per feet.
Times 7.
Right, so your first fire, you know, let's say the first fire is downtown. Fire.
Because, yes, because each truck has 7 voice coming.
One truck cannot be in two
And
places.
because they can go to
So
all
what is it?
No, 7.
Oh, so
There's
fire.
7 fires.
So
So
yeah, you're.
Oh,
You still have to.
Seven choices. The second truck has 7 choices. All the way to the 21st truck has 7 choices. That was a total of 2.
If you only send one truck to each fire, you're gonna have 14 trucks sitting in the station. So what I'm trying to get you to see is basically, this is not the way to think about it.
Okay, that's not right.
Because
Yeah.
the first fire could use one truck, which would have 21, but it could choose 2 trucks, or 3 trucks, or 4 trucks. There's a million possibilities, right?
And then for the next.
Of how many, even just the first fire, and then based on that, the second fire's choice would then be restricted, right? If the first fire took all the trucks, then you don't have any more choices. Because the first fire took only one truck, and you'd have tons of choices. So it's just way too uneven. It also doesn't really make sense. You know, this physical problem would be why the trucks are choosing fires, not fires. But this is an important thing to think about. When you're looking at other problems, that you have this kind of situation, trucks and fires, or stuffed animals and kids in a party, whatever the.
We don't know.
Which way is best for like an install floor? Are the trucks choosing the fires, or are the fires choosing the trucks? Are the kids choosing the stuffed animals, or are the stuffed animals choosing fires? You can do this with a lot of. If you.
Well, then you go down, the second truck has.
If you've never done one of these ones, that's
Yeah.
perfect. Think it might do that.
Yeah.
But what you wanna do is if you realize that this is just unwieldy to imagine right now.
Right, because the
I
first
would take a breath, I would take a step back and
fire has to be
think about this. It's
The second
natural
fire has.
an answer is, makes more sense to me. If that makes sense.
You're kind of like a way similar to how like.
It's a physical problem, so you can really start off not being so mathematical. Yeah, you sort of have to think about it, but I would say it's just.
Okay. I mean, like, part of flipping it around, actually. Like, like multi-line.
Same fire.
So you mean like 21 choose that?
That's a
21 choose that. Ah. Something like that, yeah. Yeah, exactly.
And then it's like a-
Yeah, we can track all the total phase that we take.
I don't see that immediately as first thing I think.
Oh, no, yeah, definitely. The only thing I remember is like the sum of the, like, if we did it the other way, it would be the sum of that.
Yes, yeah.
I'm not saying it's
6
good.
fire.
for
19, it would be reasonable to count that, and it's not gonna be that.
Yes.
Yeah.
It's very fire.
The two.
Okay. Good, good. Love it. Mark D. Structural hosting, each fire has exactly how many trucks. Yeah, I like it. Yeah, you just, all your trucks, use 3 of them for the first fire, then from what's left, choose 3 more of them to the second fire. So on and so forth. but it's reasonable to have them in order. There's a first fire, second fire. third
Oh,
fire.
it's like that one,
Trucks themselves,
The.
it doesn't matter what order you choose.
With like.
If I put the red, green, and blue truck in fire number one, it could have just been the blue, green, and red truck, and it's still the same outcome.
But then it becomes
Those
a-
three trucks are going to be hard. Using combinations here. Yeah, I like it. Okay, yeah, you are going to need to.
No, but I think it's a five. Right.
Yeah, you are.
Oh, there it is. Never mind. Oh.
I think you might be.
Because it's Saturday.
No, because we did pick one. Oh, no, we don't divide because.
Yeah, we don't need to do this.
They were. But somehow there was some.
There's specific spots.
No, we have to order because it's fire.
It might be the.
I guess we can't have agency fire.
It's, I think it's because.
Like it was too specific.
Yeah.
But it was
Maybe
like.
it's not. It's the problem with it, I always have. Like.
No, the fire.
Or the actually, I'm gonna say we're not.
No, no, we are ordering it, but like we pick. But then this is fine because they are distinct, and it's different from the other provinces. Because.
And I was.
There's one specific. It's gonna be like other people.
Okay. They won't,
Here's where we get the. Yeah.
I think this is fun.
Yeah. No, I agree because, fire.
Like our first one.
I didn't hear.
Okay, we can look at this one, right?
Yeah. Fire one had to be.
We're just saying, for fire one, there's 21 cars. Here, now we have to go to fire.
Right.
It's because the following reasons.
Not the same.
I'm not saying it's not order, they come and- Yeah.
No, I think other trucks could also be.
They can go to the same fire. It just matters if they're in the same, those two.
It's far too.
That's okay. It's one, well, and there's some.
That one's scratched. but-
19.
The fact that it got that dry is like.
How about?
Can I see your answer?
Yeah, there is a couple like that.
Yeah, great.
Yeah.
But it's because this one is way.
Yeah.
But I'll find ice.
Right.
Is it minus? Just 7.
Like, I have to put papers and- and then But I wish I do have to.
Yeah.
Fire and have issues.
Oh, there's another one.
Yeah.
Seven.
And then like something now.
Seven, yeah.
Oh, we just subtract the case that there are two.
It's definitely you want to do the second thing she was gonna represent, yeah, always pick the other truck. And then next time we think that we see.
Select the truck section.
One that we can do.
With that in mind, it's now.
It's specific that's slightly off of the.
I know what you're doing.
Would we choose?
Oh, yes, I think we have our 31 try. It's just one of, you're picking one of these.
You just wanna pull the guys away.
Yeah.
It was like that problem with the homework.
So what would this
Man,
be?
the
This is
woman
the first
trying to
fire.
say-
Yeah, it's
Fire
hard.
one truck
Sorry.
is two, and then the second one is-
No, wait, but the difference is that.
So what we're doing is saying, fire was really-
Yeah, yeah,
It was 7:21.
You want to-
Wait, I was thinking that like, right, it's just that,
Seven, 7.
No, they should.
I wasn't Yeah.
Oh,
I think that-
Right, like the
Fire
problem.
fires, that's the-
Yeah.
I was worried for a second. My head was like, are you-
That's seven to like seven.
The fires.
You get
So-
6
But I think
You get 6 times 7 is like.
Had seven.
I
think it's kind of like
like
digital. There's already something inside, so they're just putting everything else. So there's like
Nice.
one minute. You know what I mean? If you get my logic, it's not exactly, you know what I mean?
And then the other one, so that those were mounted up in the same time. Yes, I think.
And then
Labeling them 1, 2, 3.
Wait, I wonder.
In reality, you're not just between the seats two and the two. I can't wait.
Oh, no, I was just wondering, does it matter which one is like?
So what if the first?
There's no space at the entrance, we're just like, asking the second.
That's the violation.
The violation.
What if every truck took the fire that's downtown?
Oh,
It's not the fire.
So I just feel like
Actually, in 5:30, there's this one problem that Professor Moriarty. It's like you're distributing gifts to children, and then they're like another machine, adding kind of similar to like this is a total, and then you have to like deal with the exceptions, and it's like that's what we're at.
Yeah, so this, this area.
It just means that there's no. So.
I still think we can.
They
simplify
did,
this
this is
to
about twice. Very different.
21 times 4.
Where you have all of the digital.
Oh, no, I mean, I had written it down. No, but this for sure.
I wanted to say, so it's just funny.
Oh, we don't have that much time on. Oh, no, I have to catch up on. Oh.
So far, so.
I'm just gonna be, usually posted.
All it states, and there are two specific questions that should not be said.
Wouldn't that just mean that?
It is a huge number, but it's
Instead of 21, each having seven
It's like, I
choices
guess
to
for
go,
each situation, it could be
it's
like,
really like 20.
it's a random, like, truck stars, we don't know.
I think it looks right.
It's nice.
Seven logical, yeah. 6 spots. for the
There's
second
only
class.
7.
The other 19 trucks.
Only 7.
Yeah, I
There's
like
only
it. I like it.
Only brand.
So it's like, there's so many trucks that are probably gonna go to the same fire.
Oh, he didn't simplify it. He left it on for the 2B.
Up to you.
Purple truck, and I have no
Wait, what?
other choice, it must go wherever. the-
Oh, we actually did it differently, but we still got the same answer.
Want it.
Okay, well,
He- He did,
We talk about parties. Talk about parties.
They have to.
How's our party? 7 spots instead of the first guy. 6 spots to get back again. Together.
They have to change, they have to choose.
Because they
which
can't
ones
be-
are-
can't be-
Which ones are the same fire that they go to.
Wait, doesn't this
Not the way I thought it was.
Oh, it is 6 times 7.
Yeah, we brought the 7 in.
Okay, yes,
It is
that
kind of
actually
weird, but-
was the same answer. I personally thought of it a different way. Can I explain this other way of thinking about it?
Yeah.
I basically did it as thinking about it as tracking violations. So I took the 7 to the 21 from part C, and I said, what are the violations? The violations would be if those two specific trucks did go to the same fire. So let's say it's the green truck and the purple truck. They must go to the same fire. So now, instead of 21 trucks all getting to independently choose whichever fire they want to go to, when you come to the green truck and you ask it, which fire do you want to go to, it'll have 7 choices. Let the purple truck not get to make that choice anymore. So instead of 21 trucks getting to choose which fire they want to go to, it's actually 20 trucks. And so this is actually the same as the 7 to the 21st minus 7 to the 20th. Which is the way I think about it, but that's just what I, subtracting violations, but it is the same answer. If you calculate 7 to the 21 minus 7 to the 20, do a little algebra on that, you're gonna get that. So it's also a perfectly good way to do it. It's nice to think about, the solution in multiple ways, because it's instructive, I think, to sort of see that it is the same answer. Thinking about it as different. So it's kind of, you imagine you put together, right? The green and purple truck. So now instead of having 2 trucks each choosing a fire, they collectively have one object choosing one. So you can walk on your choice, so instead of 21. You have truck choosing fire. They only 20. So in other words. Very good thoughts that way. Yeah, that I would appreciate it. Yeah, so basically, this is one of series. And you factor out the 7.
That's what it is.
You get exactly what you're.
They have one choice. And then the night.
Yeah, so instead of 21 different trucks, choosing a fire.
Yeah.
We're only gonna have 20 trucks. Because the green and the purple truck have to go together, so they as a pair only get.
We grouped them before the
one
one.
switch fire.
Everyone is still making.
This
all
number
21
of
or something.
big subtract.
They still have to choose.
Excellent.
Yeah.
Which is technically what you're saying, that it has-
We just forgot the one.
Make sense?
Yeah.
It took me a while to get the 20.
Gluing together.
And they have one thing.
I feel like I can attend my.
They get one choice to select.
Yeah.
Exactly.
Yeah.
Hey, guys,
Oh, I mean, like.
hello,
it's on the side, but I don't-
can I, get everybody's attention? After class, I'm gonna talk to you guys for like 2 minutes, okay? I'll come back. Be
Oh,
back.
there's a lot of people.
Uh,
Don't even have-
But I only have 10 minutes left and I would like to start talking about one other thing if I could. I'm kind of like the guy who uses every second of the time. The groups did a great job, like I've been going around, for the most part, everything's looking really fantastic. The solutions to this are in Canvas, as you know, so as always, I want to ask you to follow up when you're studying for the quiz next week. These 3 group works that we've done are all, I think, good example problems to go back to as something to practice. But yeah, I like the fire trucks problem. So there's a lot to be learned from those 5 parts. And actually, the one part I should have added to this is, what if? So there's the one that the fire trucks are all distinct and each fire has to have exactly 3 trucks. That's part D, I think. What if the fire trucks were all identical and each fire had to have exactly 3 trucks? Oh, nothing nearly so deep. I have 21 identical trucks. And I have to send 3 of them to each fire. How many ways are there to do that?
Oh.
If they're all identical?
I wonder whether it- 7.
No,
Oh, same.
it's a trick question. You have 21, I have 21 identical black markers. And I've got to put 3 of them on each of 7 different tables, right? How many ways are there going to be?
There's only one way.
One way, right? I'm gonna have 3 there, I'm gonna have 3 there, basically, it's one way, if they were all identical trucks. So that would have been an interesting one. I should add that for next time. That's kind of a trick question. Anyway, I like those problems. Those are kind of fun. With the few minutes that we have left, I just wanna share a little brief start on the next thing we're gonna do. As you know, chapter 1 was just kind of an overview of combinatorics that we didn't really go over. Chapter 2 is what we just finished. Chapter 3 was the pigeonhole principle, and we're gonna jump ahead and start here just for a few minutes today, guys, starting on chapter 5. Okay, so this is gonna get us a little bit further into the book. And this is all about binomial coefficients. So I'll talk here about binomial coefficients a little bit. And these are, of course, just the expressions that we've already encountered, which is the n choose k, all right? So that's what they are. We already know how to calculate these things. N factorial divided by k factorial and also divided by n minus k factorial. So those are the so-called binomial coefficients. And what I want to do in this chapter 5, guys, is I would like to discuss the properties of, so I'm getting a little bit away from the counting strategies now, and I want to just talk about the properties of these numbers, as well as how to use them to create combinatorial identities, which are just formulas involving them. So it's just kind of taking an interest in these very special numbers for their own sake. They're obviously showing up on a lot of these counting problems that we're doing, but they're also just very interesting in their own right. And it would be, I think, remiss for me to just ignore some of the intrinsic beauty of these numbers. So that's what we're going to do. We already know, that if we take n choose k, then it's the same as n choose n minus k. This would be one example of a combinatorial identity. Okay, and you can see that if you just look at this expression, if you replace the k with n minus k, you get the same calculation, the same numerical value. But there are some other interesting formulas that I'd like to show you. So other interesting formulas, and I'm just gonna have time to maybe give you 1 or 2 of them here today, and then we'll come back to this next week as well. The first one is, this is kind of interesting. If you take n choose 0, and you add that to n choose 1, and you add that to n choose 2, and you go ... all the way up to n choose n. Now this one's gonna be hard to work with the factorial formula with because, the denominators are constantly changing. And it's gonna be hard to kind of combine these things together. So I'm not going to be as easily able to algebraically simplify this, but this is a very, very, very simple number. Oh, did everybody catch that? You stole my thunder. Yeah, maybe some of you have seen it before. It's 2 to the n. Yeah. Do we know why this is true? The 2 to the n, is actually the number of subsets of an n element set. So, if you had like set 1, 2, ... up to n, it would be the total number of subsets. Why is that? Well, each of these elements in the set can either be included or excluded from the subset. So if I'm making a subset S, it's a subset of 1 through n, I'm gonna look at each of these numbers and say, is it in S or is it not in S? That's two choices. So think of the multiplication principle, right? The number 1 is either in or out. Number 2 is either in or out. 3 is in or out. So there you have exactly two choices for each of these numbers, and it's independent from one another. So you can just get 2 to the n combinations of, or sorry, not combinations, 2 to the n subsets of this master set. That makes some sense? How can you think of the left side as also being the same thing? Sergio,
Like a subset first with 0 of the items and then 1 of the items.
that's the empty set, right? This would be subsets of size 1. So that would be singletons, right? So you'd have 1 by itself, 2 by itself, all the way up to n by itself. That's counting those, right? This one would be subsets of size 2, right? So this would be like 1 and 2, 1 and 3, 1 and 4, and dot, 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 all the way up to, n minus 1 and n. By the way, these subsets, the elements are not in order in a subset, right? They're just in a list, but there's no first element, second element, third element. It's just an unordered list. And of course, the last one would be the entire subset, the entire universal set that you were working with. So, like the justification here is more of it's not done numerically using the formula. It's done by counting something in two different ways. And what we're counting is the number of subsets of an n element set. One way of counting them is to count them according to how big they are. Subsets of size 0, subsets of size 1, subsets of size 2, and add them all up, right? The other way of counting the exact same thing is to look at the n objects themselves and say they're either in or out of the subset. Two choices, two choices, two choices, all the way down the line, and that's 2 to the n. And since you counted the same thing, their numbers have to be the same, right? This has to match with that. So it's a cool way to prove a theorem, or to prove a formula. And so that is an interesting formula, I think. Another one, I'm gonna write it down, and then maybe, because I'm out of time, I'm gonna write down this formula and then give you 5 days to think about why it should be true. Okay, let me just write it down because it's kind of famous and I want you to have something to chew on. This is the second example of an interesting formula. This one is so famous that it is called Pascal's formula. Yeah, it's a famous formula called Pascal's formula, and in the book, this is just in case you're referring to the book, theorem 5.1.1. Let me just write it down. It just says that for all n and k with 1 less than or equal to k less than or equal to n minus 1, we have the following formula. N choose k can be written as n minus 1 choose k plus n minus 1 choose k minus 1. This is Pascal's formula. This one can be proven using the factorials and simplifying the algebra of it. So if you're looking for gold star points over the weekend with me, what you can do is come back on Tuesday with a way to explain this formula that's more conceptual in the way that kind of I explained this one. Is there some way that we could imagine n choose k So this would be choosing K players for a team from a whole pool of N of them. Is there some way of thinking of that in sort of two cases that add together to give you those total number of choices? You're gonna have 5 days to think about it, and then we'll come up with an answer together next week as well.
I got it, you know.
You can tell me later. Okay.
I didn't.
Guys, I'm out of time. Thank you for your patience with me here. I'm sorry to run a little over.